All right, so let's dive into something pretty puzzling today. We've all seen pictures of planets and asteroids, right? All like, all scarred with craters, like a cosmic shooting range or something. But some of them, like this giant asteroid Vesta that NASA's Dawn mission explored, they are these weird gullies too, and that's what we're diving into today. How do these gullies even form on Vesta? And we've got two main theories about this, both pretty wild in their own way. So one idea says it's dry debris flows, like space landslides, basically, triggered by impacts, or even just, the sun baking the surface. It seems kind of reasonable, right?
Yeah, it makes sense.
But the other theory is where things get interesting. This theory says it was liquid water flowing on the surface. Wait, hold on. Water out in the vacuum of space. That's what we're going to unpack. How is that even possible?
Yeah, it's a good question.
So first, let's talk about Vesta itself. NASA's Dawn mission gave us a ton of images, and the first thing that jumps out is craters. Seriously, craters everywhere. Like Vesta has spent the last 4.6 billion years just getting pummeled by space rocks.
And those craters tell a fascinating story. They're not just evidence of a rough and tumble solar system. They actually give us some clues about how those mysterious gullies might have formed.
Okay, so how do scientists usually explain gullies on places without air?
Well, the go-to explanation has been these dry debris flows, the landslides we talked about. And it works pretty well for a lot of airless bodies. But when you look closely at Vesta, something's not quite right. The gullies there are long and winding. Some even have these lobes at the end, almost like they were carved by something. Well, flowing,
And that's where the water theory comes in, right?
Exactly. A recent study, actually, in the Planetary Science Journal, suggested that it wasn't dry debris at all, but actual liquid water that carved these gullies. And they've got lab experiments to back it up. They recreated Vesta's conditions right here on Earth.
Hold on, wait. Isn't liquid water in the vacuum of space kind of like, opening a soda bottle on a roller coaster? Just fizzes away instantly, right?
Well, yeah, that's the million-dollar question. Liquids, especially water, they do tend to vaporize very quickly in a vacuum. So trying to explain the liquid water flowing on Vesta, that's the real head-scratcher.
So what's the solution then? Did they, invent space-proof water for this experiment?
Not quite. The key ingredient here is something you probably have in your kitchen right now. Salt. Ordinary table salt. Sodium chloride.
Hold up, are we talking about sprinkling salt on Vesta to make gullies? That's even crazier than liquid water in space.
Not exactly sprinkling, but you're getting warmer. These researchers used a special chamber at JPL called DUSTIE, which basically mimics conditions on Vesta, and what they found was mind-blowing. Pure water, when exposed to that vacuum, it froze instantly. But add some salt, make it briny, and that water stayed liquid for over an hour.
An hour?
Sure.
That's longer than some of my attempts at cooking. But is that really enough time to carve out these gullies we see?
It's more than enough. See, here's where it gets fascinating. That briny water, it forms a frozen lid on top. Imagine a layer of ice, acting like a shield. It prevents that liquid underneath from instantly vaporizing, so it gives that water time to flow, to carve those channels before it eventually disappears.
Okay, I'm picturing this frozen lid, but I need a real-world comparison. Is there anything on Earth that acts like that?
Think about lava tubes. You know those tunnels formed by flowing lava? The outer layer cools and solidifies, creating a crust, while that molten lava keeps flowing inside. So this frozen lid on Vesta is kind of like that, only instead of molten rock, we have salty water. And it might not be unique to Vesta either. We think similar things could be happening, with mud volcanoes on Mars, and even icy volcanoes on Europa, one of Jupiter's moons.
Whoa. Salty water volcanoes on Europa. That's next level. But let's not get too sidetracked. We were talking about Vesta and all those craters from the Dawn mission.
Right, and remember, besides craters, Dawn also found evidence of hydrated minerals on Vesta. That points to water ice lurking beneath the surface.
So you're saying those impacts that made the craters could have also melted that ice, creating these briny flows. It's like a cosmic chain reaction.
Exactly. And to make it even more interesting, Dawn found something similar on Ceres, a dwarf planet in the asteroid belt. They found evidence of subsurface brine there, too.
Hold on. Are we saying there could be salty, slushy oceans hiding under the surface of these seemingly dry objects?
It's a possibility, and a pretty mind-blowing one at that. This research on Vesta is opening up a whole new world of possibilities for where we might find liquid water and maybe even life in our solar system.
Okay, my mind is officially blown. But let's rewind a bit. We've got these two competing theories for the gullies on Vesta. Dry debris flows versus salty water flows. What exactly is the evidence for each? And what makes that salty water theory so compelling? Despite sounding like something straight out of science fiction, We'll break it all down when we come back.
So let's unpack the evidence a bit. In the dry debris flow corner, we've got the fact that impacts are incredibly common in the solar system, and Vesta has been bombarded for billions of years, so it's totally reasonable to think that those impacts could have dislodged material, creating those gullies.
So basically, space rocks hit Vesta. Things fall downhill. Gullies form. Simple as that.
Well, it's not quite that simple. Temperature swings on a world without an atmosphere can also cause the surface to expand and contract, leading to fractures and, you guessed it, more debris flows. So there are multiple ways dry debris could explain those features.
All right, so the dry debris theory has some points in its favor, but you said something was off about Vesta's gullies. What makes the salty water theory so compelling?
The shapes. Dry debris flows. They usually make these short, stubby gullies, but the ones on Vesta are long and winding, sometimes even branching out with lobes at the ends, like something was flowing and carving them out over time.
Okay, I see what you mean. The salty water idea fits those shapes better. But are we really basing this whole theory on like a few lab results? It seems like a big leap to go from a chamber on Earth to a whole asteroid.
It is a leap, but not a leap of faith. Remember, the Dawn mission found those hydrated minerals, suggesting there's water ice beneath Vesta's surface. And those impacts we talked about, they generate a lot of heat, more than enough to melt that ice and potentially create those briny flows.
So we've got impacts creating the heat, melting that ice, and the salt keeping it liquid long enough to carve those gullies. It's like a perfect storm for salty water shenanigans.
Exactly. And remember how Dawn found evidence of subsurface brine on Series 2? This might not be a one-off event. We could be looking at a pattern here. A hint that briny flows might be more common on airless bodies than we ever imagined.
Hold on. If these flows happen on other asteroids, could they be happening right now? Like as we speak?
Now that's a fascinating question. We don't know for sure, but it's definitely possible. And it raises even more questions. How widespread are these subsurface brines? Could they be shaping landscapes on other worlds we've only seen from afar?
I'm getting serious sci-fi vibes here. But before we get too carried away, let's play devil's advocate for a minute. Are there any, weaknesses or challenges to this salty water theory? I mean, it does sound pretty out there.
Of course. Science is all about questioning and testing ideas. And the biggest challenge here is that we haven't actually seen those briny flows on Vesta. We're inferring their existence based on the gullies. And the data from the Dawn mission...
So it's like a cosmic detective case.
Yeah.
But we're missing the smoking gun.
Exactly. We need more data, more observations to confirm whether those flows actually happened. Imagine if we could land a rover on Vesta, one with instruments that could analyze the composition of those gully deposits. That would be a game changer.
Okay, a Vesta rover is officially on my space exploration wish list. But until then, how do we get more clues to solve this mystery?
Well, we can keep refining our models, conducting more lab experiments like the one with DUSTIE, and look for similar features on other airless bodies. The more data we gather, the closer we'll get to cracking this case.
This is what I love about science. Every answer leads to more questions. More avenues to explore. It's like peeling back layers of an onion. Except this onion is a giant asteroid, and the layers could be hiding salty water, and maybe even life. Okay, maybe I'm getting ahead of myself again. Let's bring it back to Earth for a second. What are the implications of this research for our understanding of water in the solar system? I mean, we're finding it in the most unexpected places.
It's true. Water, or at least the ingredients for it, seems to be far more common in our solar system than we previously thought. And that has huge implications. For our search for life beyond Earth, we used to think liquid water was this rare and precious commodity, limited to a few planets and moons, but now it seems like it might be lurking beneath the surface of countless airless bodies, just waiting to be discovered.
Okay, so salty water might be flowing on Vesta, and maybe other objects too. But why salty water specifically? Why not just plain H2O? Does the salt actually matter in all of this? Or is it just like a cosmic coincidence?
Ah, that's a great question. It really gets to the heart of why this whole salty water theory. It's so intriguing. See, salt acts like a natural antifreeze. It lowers the freezing point of water.
Like when we sprinkle salt on icy roads here on Earth.
Exactly. On Vesta, that salt in that subsurface brine, it does the same thing. It keeps the water from freezing solid, even in those incredibly cold and airless conditions.
So the salt's kind of like a guardian, protecting the liquid water and letting it flow. But But you're saying it does even more than that.
Oh, absolutely. Salt also makes that water more stable. Remember that frozen lid we talked about? Well, the salt actually strengthens that lid, makes it more resistant to breaking down. It's like adding extra beams to a roof to keep it from collapsing. And in this case, that collapse would be the water vaporizing away into space.
Wow, so salt isn't just a table condiment. It's like a key ingredient for potential liquid water on other worlds. Who knew?
It just goes to show that sometimes the most common things can have the most extraordinary effects. And it reminds us that we need to consider all the factors, even the seemingly small ones, when trying to understand these complex planetary processes.
Okay, I think I'm getting a handle on the salty water business, but let's zoom out for a moment. Talk about the bigger picture. What did these findings on Vesta tell us about the possibility of life beyond Earth? Is salty water enough to get the job done?
Well, life as we know it needs liquid water. There's no doubt about that. It's the essential ingredient for all those chemical reactions that make life possible. So finding evidence of liquid water in these unexpected places, that's incredibly exciting. But whether that water is actually habitable, that's a whole other question.
So what else would we need for like a briny environment like this to support life? What makes a place truly livable?
Well, first off, you need an energy source. Life needs energy to do its thing, to grow, to reproduce. You know the basics of being alive. Here on Earth, most life gets its energy from sunlight. But on a place like Vesta, sunlight can be pretty brutal. So if there is life there, it might have to rely on other sources of energy, maybe chemical reactions happening within that briny water itself.
So we're talking about like extremophiles, those tough little microbes that thrive in places where nothing else can survive, like those deep-sea vent creatures that love heat and chemicals and stuff.
Exactly. Extremophiles on Earth have shown us that life is amazingly adaptable. It can exist in conditions that would be deadly to most other organisms, so it's certainly possible that similar life forms could exist in those briny environments on Vesta or other airless bodies.
This is blowing my mind. We started with gullies on an asteroid, and now we're talking about extremophiles and the possibility of life beyond Earth. It's incredible how one discovery can lead to so many new questions.
That's the beauty of science. It's a journey of constant discovery. Every answer we find just opens up more avenues to explore, and that's what makes it so endlessly fascinating.
So for our listeners out there, what's like the big takeaway from today's deep dive? What should they be thinking about as they go about their day?
I'd say the biggest takeaway is that our solar system is full of surprises. We're always learning new things, challenging our assumptions, and pushing the boundaries of what we thought was possible. And this discovery of potential salty water flows on Vesta. It's a perfect example of that. It reminds us that we still have so much to learn, so much to explore, and who knows what other incredible discoveries are waiting for us out there in the vastness of space.
Well said. And for anyone who wants to like delve deeper into this fascinating topic, we highly recommend checking out the full research article in the Planetary Science Journal. We'll include the link in the show notes. And with that, we'll wrap up our deep dive into the mysterious gullies of Vesta. Until next time, keep those minds curious and those imaginations soaring.